Okay, in the last class we kind of discussed about periodic properties. We just started about the periodic table. So we saw that there are two important things that you have to keep in mind. The first is the nuclear charge, which is just the number of protons or the charge on the nucleus, and number of shells. Okay, so nuclear charge increases from left to right, also increases from top to bottom. Number of shells remain the same from left to right. Any doubts with this statement that the number of shells in a period remains the same? So everyone, does anyone have any doubt? So if you're in period 3, what's the number of shells? 3, right? So it's simple, and number of shells increases from top to bottom. Now, within these two, we looked at a property called atomic size. An atomic size is defined in geochemistry or in chemistry as the average distance between two atoms. So if you have an atom here, you have an atom here, you connect these two, this is, say, distance d. So from one nucleus, from the nucleus of one atom to the nucleus of other atom, connect these two. Half of that is called the atomic radius. So this is called the atomic radius. Okay? Now, what happens to the atomic? So I just gave you a definition, so nothing spectacular. I just showed you, okay, when I'm talking about atomic size, I'm talking about atomic radius, because when you see, when you look at a table online, you can actually see that there are tables in which atomic radiuses of different elements are listed. Okay, the people who have laptops can also quickly check. And Brian, can you check and give me some atomic radiuses from? You will find it anywhere. Like just do a Google search, get a tabular. So in tabular form, they'll provide a list of atomic radiuses, and this is just like defined as this. So how will you measure the atomic radius? By this. And what happens to the atomic radius when you move from left to right in a period? What happens?
Increases. Bigger.
Sorry?
Increases.
Okay, why? Why does it increase? What are the things on which the atomic size will be dependent on?
Protons and neutrons.
Do you agree?
I was going to say it's orbitals.
Orbitals, or say, let's simplify it, say orbits.
Okay, orbits.
Okay, so from left to right, what happens to the orbits?
They increase, I guess, or...
Do they increase?
No, they actually...
They're remaining the same,
remain the same.
right? So atomic size is dependent on two things. You said the orbits, okay, which remain the same when you go from left to right. And what is the other thing?
Electrons?
Why? So if you're saying electrons, you have to justify. You cannot guess. It might be true, but you have to know that you said the right answer.
I guess it's dependent on the electrons being filled in the orbits.
So we have the atom, something like this. So we have the nucleus, very small, and we have the electrons in here, right? Now the size, now this distance will depend on what? You said electrons, yes.
It's like stability, I guess?
It is. It depends on the stability. Yes, Courtney.
you know, like you said that last class, the further out it is, the less pull it has on the electrons that are like in the outer shell. So would it be
Yeah, so like,
attraction?
Hunter, does that sound correct? So what does it depend on? You said electrons, Courtney said protons. Anyone can chime in? You have to think what's the so when you're thinking about size, you're thinking about essentially this radius, right? It's like half of that. So you're essentially talking about this radius. If the number of shells is remaining same in that period, so is this getting pulled in, pulled out, no effect as you're filling in the electrons? What's happening? Because the shell is constant, right? So if you just take an example of something like this, so what's the number of shells in all these three? What do you have to do? You have to write the electronic configuration. Can you quickly write down the electronic configuration? And this is 11. And you can do the Bohr-Breeze.
2p6, 1s1.
3s1.
3s1.
1s2, 2s2, 2p6, 3s1. So how many shells? 3, right? So this is. And what's the electronic configuration for Mg?
That, but with 3s2.
Right? Just a 3s2, right? Just a 3s2. So what's the number of shells in here? 3, right? Same for this. All of them are from period number 3. So the number of shells in all of these are constant. So this is the third shell. All of them have 3. All of them have the same orbit. Now, when you keep on filling in electrons, so this went from 11 protons here. So let's draw sodium. So sodium will be 11 protons here and 1 electron, say, here. Mg will be 12 protons here and 2 electrons. Aluminium will be 13 protons inside and 3 electrons in the orbit. Now think what is happening to this radius. Just think about this radius, because that is atomic size. What is the radius?
Decreasing.
Why?
Distance between is decreasing.
The distance between what?
It's compacting more. The distance between the electrons is decreasing as well.
This distance is compacting, you say? And why is that?
Because charge and energy states changing.
Because this is becoming more proton rich. What happens when it becomes more proton rich? It's going to attract more or attract less these electrons?
Attract more.
It's going to attract more. So when it's going to attract more, what happens to the radius? It's closing in, right? Does that make sense? Because if it doesn't, nothing that we'll talk about after this is not going to make sense. If you do not understand this, clarify it here. It's not an easy concept. Once you understand it, it becomes easy. But please clarify if you have any doubts in here, because other people in the class might not be thinking like you are thinking.
I feel like I had a more kind of intuitive understanding as far as, more protons, you might have a larger, more dense nucleus. And that is kind of, if the orbit is constant, and it's not expanding, if you have a larger nucleus, then you might imagine that the distance between the protons and the electrons in the orbits are decreasing.
Okay, so you have a very different idea. Did everyone understand what Venus said? He's saying that the radius, that's the way he understood it. Maybe he's right, who knows. He's saying since you're filling in more protons, you're making the nucleus a little bit larger. And that's why you are decreasing. But did anyone find like a actual number? Okay, can we get some numbers?
Sodium is 190. And then also
190 what?
it's just the radius.
What and units?
Nanometers, isn't it?
I believe it doesn't tell me on this chart. I believe it's nanometers, isn't it? I just
It seems like a little big for nanometer.
It's 0.190 nanometers.
0 point? Right, okay.
That's for the atomic radius.
Right, okay. Okay, so 1.9 angstroms. Right? So angstrom is 10 to the power minus 10.
and that would put fluorine at
Okay, let me go back to a little simpler thing, which many of you might have confused, because the conversion between, is everyone comfortable using these conversion between the units? For those who have forgotten, so it's deci, centi, milli, micro. So this means -1, -2, -3, -6, -9, 12, 15, 18. So this is 1, 2, 3. We don't have a 4 or 5. So from here, it goes on multiples of 3. And any time you have a nano written or a milli written in front of anything, you just think this. So this is a way of converting numbers into words. That was the whole idea about it. So if you have microliters, it just means, so if you have 3 microliters written somewhere, you just write 10 to the power minus 6 liters, and that's it. That's what it means. So when you have this, so this is micro. You just write this. This is a very simple concept, but this will help you a lot when we discuss about concentrations and things like that in the aqueous geochemistry module. Okay. The other part is deca, hecto, kilo, mega, giga, tera, peta, exa. So but let's keep it here. Just think, this is just a word. This thing is just a word and this thing just a number. So like they interchange, and that's it. Now, when you say, you don't see an angstrom there, so I said 1.9 angstrom. This just means 1.9 into 10 to the power minus 10 meters. So angstrom is a unit which means 10 to the power minus 10 meters. And nothing else. This cannot be liters or any other unit. This is just a length unit and 10 to the power minus 10. I don't know why this was used, but this is being used. And the size of an atom is this. This is the size of the atom. Okay, when you're talking about an atom with the nucleus here and the atom, this radius is 10 to the power minus 10 meters magnitude, like roughly. This is the atomic scale. You cannot see that. Another question. Why can't you see atoms? It is tiny, but I mean, yeah, you cannot beat that. Okay, so I wouldn't be able to beat it that now. But when we discuss about X-rays, so there's another question, like how can X-rays Okay, the thing is, if our eyes were, which wavelength does our eyes function? Just the visible. And visible means there is a wavelength, right? It's like a 300 micrometers to 600, 700, something like that, right? So we are in the visible range. And there is a wavelength. Can anyone give the wavelength? I don't know, 300 micrometers or something like that. Or 650. Yeah, in that range. And what does micro means? So this is the wavelength. Our eyes cannot see things below this. Because visible, our eyes can only see things that the visible light can interact with. I'm sorry, I digress with these things, but these things are interesting, and like sometimes, yeah, I mean, I do these kind of things. I apologize, but so your eyes cannot see atoms because your eyes can only see in the visible range, or your eyes can only see those things that the visible light can interact with. Okay? Now, visible light can only interact with things which are that or greater than that. So, the wavelength is the distance between crest to crest, right? So this is the wavelength. So this is of the order of, say, 300 into 10 to the power minus 6 meters. So anything that is bigger than this wavelength, suppose this thing, so this thing, obviously, the dimensions of this thing is bigger than 300 into 10 to the power minus 6, and visible light can interact with this. If the things are really small, visible light will not be able to interact with the things which are smaller than that. Okay? Any wavelength will not be able to interact with anything that is smaller than its wavelength. Any electromagnetic radiation. Okay? You won't be able to. So atoms are angstrom size. So you need a wavelength which is angstrom size for that being able to see it. X-rays do that. So X-rays have wavelengths which are in this order. Okay? And that's why you are able to see atoms. Okay? Now, this is 10 to the power minus 10 meters. So a quick conversion, this is, we'll do it again and again, and that's why. So when I wrote 1.9 angstroms, this means 1.9 times the angstrom is just a number. I just removed this and wrote this. You can also, can you write this as 10 to the power minus 1 times 10 to the power minus 9? Can you write that? Can you write 10 to the power minus 10 as 10 to the power minus 1 times 10 to the power minus 9? Remember indices? 10 to the power a plus b is basically 10 to the power a times 10 to the power b. And that is why if you have, say, 2 to the power 3, this means something like this. So if you have 10 to the power minus 10, you can write 10 to the power minus 1, 10 to the power minus 9. And this I can write 0.19 into 10 to the power minus 9 meters. 1.9 times 10 to the power minus 1 is this, right? Or am I making some mistake? Yeah, is it okay? No? Okay. What does this mean? This, right? minus, isn't it? Or no? It is. So can I not write, that's what I wrote here, right? So can I write nanometers, right? So it's just a conversion, doesn't necessarily impact our discussion today, but please keep these things in mind. The conversions from one to another, you have to be good at it, because that's basic things that you will need in aqueous geochemistry, these conversions. Okay, now remember that the atomic size is this. The nucleus is something of this order. Okay, just the nucleus. So Venus, now you said that since you're getting more protons, do you think that you can affect the size of the atom? You won't, because the 5 orders of magnitude here and there. So just adding the protons might increase the size, but that will not affect, right? Because when Brian told the size, he just told it to like 1 decimal place, or 0.19. You'll have to go to 5th significant or 6th significant to make a difference. So it's not going to make. Are you convinced? Okay. So sodium was 1.9 angstroms. So that is the atomic size or the nucleus size? Sorry? That is the atomic radius. That's not the nucleus radius. Okay. Do you have magnesium?
0.16 nanometers, or I guess
1.6. Okay. Aluminium?
0.143 nanometers.
Okay, so there is a trend. But can you go to the last, what's the last element here? Who can tell? Argon, yes. What's the size for argon?
.098 nanometers. So
0.09. 0.098. Is it correct?
that's what it says. That's what the internet tells me.
Is it, so are you looking from the same table that gave you the other numbers?
I just Googled it and I got the same thing.
We're just Googling it. It says the atomic radius of argon is 0.098.
Okay. For now, let's keep it at here. But my idea is to make you understand that atomic size is decreasing from left to right in a period. Does anyone have any doubt regarding that? Or everyone is convinced that atomic size decreases from left to right in a periodic table? Any doubts? And why does it decrease?
The relationship between the amount of orbitals in the protons in the nucleus, and then the attraction that the protons have on the electron.
So yes, atomic size depends on the number of orbits and the nuclear charge. So the number of orbits is not changing when you're going from left to right, but what is happening to the nuclear charge when you're going from left to right? And what is that doing to make the size smaller?
It's pulling the electrons in closer to it.
It is pulling the electron. So you have to understand that this one electron, when this one electron was getting pulled in, it was getting pulled in by 11 protons. These electrons, when they are getting pulled in, are getting pulled in by 12 protons. And this, when they are getting attracted, they're getting attracted by 13 protons. So when you are attracted by more number of protons, your size is decreasing. So atomic size is decreasing when you're going from left to right. And it is increasing when you're going from top to bottom. Why? My doubt is, when you are going from top to bottom in a group, the nuclear charge is increasing. So why isn't the size decreasing? Like it was, the nuclear charge was increasing from left to right, the size decreased. The nuclear charge is also increasing from left to right by a lot. Why isn't the size decreasing? And that has a substantially more effect than the incremental effect that comes in with the pulling. So when you are adding more shells, so when you are going from top to bottom, like there's an immediate increase in the number of shells, and that increases the size. And then you are again decreasing. And then you're again increasing when you're moving out, then you're again decreasing. And then you're again increasing the size and decreasing. But generally, this is the trend. Does anyone have any problems? I will bring in exact data from tables so that we have something to compare. Okay? Now, since we understood this, let's go to the next one that we discussed, which was ionization enthalpy. Now, tell me, ionization enthalpy, was it an exothermic process or an endothermic process? Does anyone have? Does everyone agree with Courtney? Can be both. Okay.
Depending on the element that you're looking at.